Alright, so for number 9 and 10, this is going to be a little different because what you'll notice is that you've got your initial starting point. You do have a percentage of depreciation, which is obviously decay, so we're going down a percentage, but we're not told when something is going to happen. We're told what that something needs to be. So this is different, and you can actually only solve this for t when you know how to use logarithms, but you guys aren't there yet. That's one of the things we're going to learn. It's going to be the last thing that we learn about exponential functions. How do we solve for this? Now, what you can do is kind of do it using kind of like to strong arm it, okay? And what we do is we basically clear all of our y equals, okay? And you can do this even if you know logarithms, like if you want to kind of, if you forget how to use logarithms, you can always use this, but you're going to need to know how to do logarithms on the test. But what we're going to do is we're going to write this function inside the calculator, but we're going to use x instead of t for time. Now what this does is the calculator will calculate all values of x, okay? And then you want to look into the tables and you want to find out when does it actually equal this amount, okay? This is the only way to do it thus far without logarithms. So I'm going to go to my table, which is second graph here, okay? And you can see that it's not very fine, okay? Looks like I'm looking for, let's see here. Let me double check. Whoa, make sure I got that right. 22,000. And when is it going to equal depreciate? It's 0.08. Okay, yeah, so go back to the table. And you can see that it's decreasing, but you can kind of scroll down here and see, oh, right there. All right, it looks like it's actually, I didn't have to change my table set at all. It looks like it's going to be 18 years. If I push over, I'll see that it actually is perfectly that number. So it looks like it's exactly 18 years. So A is the answer. It's none of those. Okay, you can see 18 years. Now, again, the calculator is figuring out how much it's going to be after each year. And we can get finer and finer if we need to. Okay, this guy's the same thing. Okay, go to y equals, and we're looking for time. For us, that's how many bounces. Now, in this case, it is actually bounces. Most of the time, it's time. Okay, but we want to know each bounce it loses almost 16%. So let's change this guy. We're going to go ahead and do 104, and I think you really should do this a few times so that you know that this is how you solve these types of problems. And it's basically going to be the difference between getting an A on the quiz or a B on the quiz. So it's gonna be a letter grade. So make sure that you know how to do this. And like you make silly mistakes like that by not making that an exponent, then your table is going to be all whacked. Okay. So let's go ahead and go to second table. And you see the function changed, and we are looking for 3.26 right there, exactly 20. If I go there, you see that they rounded to 3.26, so that's going to be exactly 20 bounces. And unfortunately, that is also a none of these. Okay. All right. Now the rest is pretty much ease. Okay. So now what we're going to do here is we're going to look at this E. coli bacteria. Now, anything that involves bacteria or kind of a natural gradual progression, anything dealing with nature, you're pretty much going to have like continuous growth rate or decay rate. So what you'll notice here is that this guy has got a continuous growth rate of 2%. So this is the PERT formula if it says continuous. So 2% is right there. There's our E, that very lovely magic number here. And our principal amount is 100 million. And then our time is actually 10 minutes. Okay, and it is 2% per minute. So we can just throw in a 10 for T there. And you can see that it's perfectly laid out for us. And that's going to equal 122.1 million. That's already done in the calculator. That's all set. Okay, now let me kind of show you a mistake that I made. I don't know if you can spot this. This is the same process, continuous rate of 0.02%. Start off with 57.1. The temperature is cooling down, okay, and it's after 8 minutes. So when I punch this into the calculator, I got like 68 point something. So I immediately circled C. But what is the matter with this? Well, the issue here is that this is actually decreasing. This is a decay model. So if the continuous rate is decreasing, that means that my rate, just like how I subtract here, okay, I need to have a negative rate here. So when I put in a negative right here and punch that into the calculator, I will go down to 48.7 degrees, which makes sense. After 8 minutes, they should decrease in temperature because it's quite cold out. Okay, it's freezing. It's 32 degrees Fahrenheit. Okay? All right, so watch out for that. That's going to play out in the next couple problems. Here, this guy has a growth rate of 2%, so we got 0.02. It does say exponentially. I'm sorry, it says continuous, so we have the E. We're going to start off 152. We're going to go ahead and do 12.14 minutes, and this is 2% per minute. So this plays out perfectly. Punch that into the calculator, you'll get D. Here, I wasn't going to make that same mistake twice. I did see that it was decay. It's dropping by 43%, so quite a bit, okay, per 1,000 years, so maybe not quite so much. So it looks like, though, they did give this in thousands of years. So I can directly put a 12.6 right here, okay, because that is in thousands. So 1,000 times that, and this guy is going to, you're going to have about 3.17 ounces if you punch that into a calculator. All right.